Now we're going to talk about continuity. And we remember that evaluating limits of continuous function of a single variable is easy, and the same logic can be extended to the functions of two variables. So let's start with the definition. We have a function of two variables is called continuous at a point AB if limit of function f of x at point AB equals f of AB. We say that this function is continuous if it is continuous at every point AB in the domain, right? So pretty much the same as for the function of one variable. So the meaning of continuity, the intuitive meaning, is that the point changes, point xy changes by a small amount, then the value of f of xy is also going to change by a small amount. So the surface that means that the surface that is the graph of a continuous function has no holes or breaks. So before we had a curve, now we have a surface. Using the properties of limits, we know that we can see that the sums, differences, products, quotients of continuous functions are continuous on their domains as well. And we're going to look at examples of continuous functions. So the first one is a polynomial function of two variables, or we can just call it polynomial for short. It's a sum of terms in the form of x times y to whatever exponents multiplied by some constant, right? So rational function is a ratio of polynomials. So I have an example of a polynomial function on the left. I have an example of a rational function on the left. And the limits in our definition show that the both of the functions are going to be continuous, since any polynomial can be built up out of single functions, x, y, and just constants by multiplication and addition. That means that all the polynomials are continuous in the 2D space, and all the rational functions are also continuous on the domain, right? We will have to think about the domain in this case. Example number 5. We need to evaluate limit of this polynomial function. Well, we already know that the function is a polynomial, so it must be continuous everywhere. So that means that our solution is simply to plug in 1 instead of x and 2 instead of y. And we're just using direct substitution. So to calculate limit of our function, we're going to plug in 1 and 2 instead of xy. Xy approaches to 1, 2. So we have 1 squared y cube minus 1 cube, 2 instead of y, I'm writing down. Okay. 2 cube minus 1 cube, 2 squared plus 3 times 1 plus 2 times 2. Almost said y again. And now when we simplify, we're going to get 8 minus, what is it, 4 plus 3 plus 4. 4 and 4 cancels out equals 11. Oh, hi, puppy. My puppy is here again. That's example 5. Moving on to example 6. Example 6, very similar. Where is the function continuous? We know that function is discontinuous at 0, 0 because it is not defined there. And that means that since f is a rational function, it's going to be continuous on its domain. So our solution is going to be function is continuous on the domain x, y, such that x, y does not equal 0, 0. Or better yet, it's on the domain which is equal, like this. Example 7. In here we have the function that is defined as x squared minus y squared. It's like f of x, right? When xy does not equal 0. And then we defined it as a 0 if xy equals 0, 0. However, g is still discontinuous, because if I write limit of my function g of xy as x, y approaches 0. 0, the limit does not exist. That was our very first example. Limit does not exist, so the function is discontinuous. In example number 8, we have a function, again, a piecewise function given to us by two equations. We know that the function is going to be continuous for x, y not being equal to 0 because it is a rational function. And also from example number 4, we know that limit of our function f of x, y as x, y approaches 0, 0 is going to be equal limit of 3x squared y over x squared plus y squared as x, y approaches 0, 0. And that limit is 0, and it is equal f of 0, 0. So that means that this function is continuous at point 0, 0, and it is continuous on R2. And the diagram that comes with it. And from this diagram, we can see that the function doesn't have any holes. It is continuous everywhere because we defined it over here, and then it is continuous. Um, just for the functions, just the same as for the functions of one variable, composition of functions is another way of combining two continuous functions. Which means that if f is a continuous function of two variables and another function g is a continuous function of a single variable that is defined on the range of f, then the composite function is going to be a continuous function as well. So let me write it down. F is the function of two variables, g is the function of one variable, so I can say then g of f of x, y, right? F of x, y, two variables, f is just one variable, is going to be equal some function h of x, y, and that is going to be, or in other words, h is g of f composite or composite function. H is also going to be a continuous function. Example number 9, where is the function h of x, y equals arctangent y over x continuous? The function, we know that y over x is a rational function. Solution. So y over x is a rational function, and that means it's continuous everywhere except for the line x equals 0. Okay, rational. Y over x is a rational function. It is continuous everywhere except the line x equals 0. And then function g of x, so that's going to be f of x, y. And then the function g of x is going to be arctangent x, arctangent x. That one is also continuous everywhere. So that means that the composite function g of f of x, y, I should have changed the variable. I'm going to make it into theta. It's going to be my theta, whatever. So then g of f of x, y is going to be equal arctangent of y over x. So that is h of x, y. And this function has to be continuous everywhere except x equals 0. So I'm going to show you a graph. So this diagram shows the break in the graph of our function h, where x equals 0, so above the y-axis. We can see the break here.